Good afternoon, Tech Nation. Thank you all for participating in today's webinar. We are thrilled with the great turnout today with over 520 attendees pre-registered. A few notes before we begin. Earlier today, registrants were emailed a Webinar Wednesday workbook. If you did not receive a copy, you can download a copy in the handout section of your webinar dashboard. Today's webinar, all lines will be muted, but you can submit questions during the presentation by using the questions or chat feature on your dashboard. If you are having difficulty, please email us at webinar@mdpublishing.com. Today's webinar is eligible for 0.1 CE credits from the ICC. To obtain your certificate of attendance, you must complete the post-webinar survey at the conclusion of today's presentation. This survey will appear immediately on your computer screen at the conclusion of the webinar. Certificates will be mailed out on or before August 19th. If you do not receive the survey, please email us at webinar@mdpublishing.com. Don't forget that many of the same speakers and presentations from our Webinar Wednesday series are featured at our annual trade shows. Our next trade show is the MD Expo, which will be held October 21st to the 23rd at the Red Rock Resort in Las Vegas. A VIP pass for the hospital employees who are on today's call was provided in today's webinar workbook, Compliments of Conquest Imaging. You can register for the event by visiting mdexposhow.com. TechNation would like to thank our sponsor today, Conquest Imaging. Conquest Imaging is the largest supplier of ultrasound parts, probes, and transducers, as well as repair, training, service, and free 24/7 technical support. Their exclusive Quality Assurance 360 program ensures that you not only get a part that performs to OEM specifications upon installation, but also outlasts the competition. Conquest Imaging, because quality matters. For more information, visit conquestimaging.com. Our presenter today is Matt Tamore. Matt is the Vice President of Sales, Marketing, and Training for Conquest Imaging. Matt obtained his Bachelor of Applied Science and has over 29 years of experience in ultrasound service, training, technical support, research and development, sales, marketing, and clinical applications. Matt, you may begin whenever you're ready.
Thank you, Kristen. Good afternoon, Tech Nation. I wanted to add a little bit to that introduction. As Kristen mentioned, I've been in the ultrasound business for 29 years. The majority of that was as a service engineer. And during that time, one of the things that I noticed was that there were a lot of good service engineers out there, but very few of them knew how to operate the machine, knew how to create an image, knew how to understand images, and knew how to tune images. And so my wife, who is a ARDMS registered sonographer, and I created this class we started with our internal service engineers and some of our internal salespeople, and we've done it for a few audiences. And unfortunately, for you folks, we're unable to do the live scanning portion, which is actually the most fun. We get to actually get gel on a probe and scan ourselves. But I am available to do that for organizations if requested. So you all have my contact information if you would like this presentation in person, and where we do include the live scanning portion, please contact me. So let's get started. So why do I need to know this? Why do I care about applications if I'm just servicing this system? Customer confidence. When you can go into a room and scan with a transducer and try and identify what a customer's talking about regarding image quality, it immediately raises their confidence in you. I'm actually off-site today at a customer location, and a couple hours ago we were actually up in the clinical department and talking to the ultrasound supervisor, and he was talking about a noise problem, and we went over to the machine, and I immediately lifted up my shirt, put some gel on a probe, and started scanning with the machine, and we were able to reproduce the noise. And immediately you could tell that this gentleman's confidence in me went up exponentially, even though he's never met me before. He knew I understood how to operate this machine. So customer confidence is huge. Differentiate between applications issue and malfunction. Image quality problems, when reported, typically are not a result of a malfunction of the machine. They're typically a result of the system not being set properly. And so the material that we're going to cover today will help you differentiate between a system setting and a potential malfunction. The ability to test a system clinically. There's a lot of times where a system will seem operational, it will pass diagnostics, it will power up just fine, but when you actually start scanning, you can pick up noise or image artifacts or things like that. And so the ability to test a system clinically as well as technically makes you a much more complete service engineer. You are your own phantom. Ultrasound mimicking phantoms or tissue mimicking phantoms are available out there, but to be able to understand your body and to be able to scan yourself, it allows you to test machines in ways that you can't with a phantom. And know the language of the sonographer. Over the years, when I've had images described to me by sonographers, and again, my wife is one of them, I've heard the words mushy, yucky, grainy, washed out, contrasty, things like that. And so understanding the language of the sonographer will help you remedy image quality issues. And I asked the question, would you trust a mechanic who cannot operate an automobile? So understanding how to fix these machines is only part of the job. I think what differentiates a good service engineer from a great one is somebody who understands how to operate these machines. The first thing we want to do is we want to evaluate the monitor display settings. If the system main display is not set properly, everything else is pretty much going to be skewed. And so when evaluating system image quality, you want to ensure that the monitor or main display, whether it's a CRT or an LCD, is set properly. What you're looking at on the screen right now is actually a picture of my liver and kidney. The football-shaped object is my kidney. All the area to the left is liver, and then that bright white stripe that you see down in the bottom quarter of the image, the bottom left, is actually my diaphragm. And so I would put an image up on the screen, and then what you want to do is you want to look at that grayscale bar on the left-hand side. So what we want to do is we want to check the monitor or display contrast and brightness settings. First thing you want to do is adjust the room lighting to typical scanning room intensity. Ultrasound rooms are typically very dark, and so you want to adjust the room lighting to simulate the room lighting when a scan is being performed. And then you want to use that grayscale bar to adjust the brightness. And what you want to do is typically grayscale bars, they're typically graduated. Some are stepped, some are graduated, but look for the very bottom of the bar. You want to bring the background brightness up to the point where it's a very light gray where you can see the entire bar, and then you start bringing it down again where the bottom of the bar is just barely visible. And when the bottom of the bar is just barely visible, at that point you have the brightness or the background set properly. And at that point you want to examine the contrast. Make sure looking at the top of the bar and at the text on the screen that the whites are white, but they're not blooming or blooming over the pixels that they encompass. This is actually a requirement for accreditation nowadays. I've written articles for TechNation and given presentations at various trade shows regarding ACR accreditation. ACR is now requiring that the system main display and actually the interpretation display, if on site, is evaluated. And so this is now a requirement for ACR accreditation. Question, and I'm going to throw this out here. This is something I always ask when I teach this class. Does adjusting the system display, or the main display of the system, setting affect the image presentation on a PACS display? And I want you to email your answer to me at my email address there, mtamori@conquestimaging.com, with your answer, and I want an explanation. The first 10 correct answers after 4 p.m. Eastern today, because I don't want anybody doing it now, will receive a $5 Starbucks card. One other thing I will caution you about is prior to adjusting a sonographer's display is verify with them that they're okay with you doing that. Sonographers are very touchy about their systems, and if you make any changes to them without their approval, it could create a problem for you. So, let them know that, Mr. or Mrs. Sonographer, I'm looking at your display and it appears to be off. Here's what I'd like to do, and show them, and make sure they're okay with that, and adjust it accordingly. Presets. Ultrasound systems have many presets. These presets are set for specific body types or specific types of exams. What you can see here is I have just a blank display, and it shows that we have a breast preset chosen. Well, under, say, a breast preset, we may have 30 or 40 different types of variables that go into that preset. Each one is specific to a body part or body type, and dozens of settings make up each preset. They are customized and extremely difficult to restore manually. If any of you are technician readers, which I'm hoping most of you are, I've written multitudes of articles in there, and about half of them talk about making system backups. It is critical that all these settings that are in these machines are backed up. To restore them manually requires going on site and sitting down with a sonographer and going through all the different types of exams and manually tuning the machine. Each sonographer is different. Each system's a little bit different, and factory presets are never good, and so each system does have custom presets. So you want to make sure that you back up and back up again. Again, if any of you read any of my articles, you'll see that I'm a huge proponent of backing up. Every system I've ever worked on has multitudes of backups, and that is to ensure that these presets are saved, and it also mitigates downtime. So let's talk about transducer and probe type. There's different probes, and I'm going to use the term transducers and probes. I'm going to interchange those. Same thing, just different term. They have different formats for different applications. We have linear probes, curvilinear probes, and then we have sector or vector probes. Those are the three main types. And here's what the formats look like. If you look at our linear probe, the linear probe is typically used for vascular studies or small parts. And small parts is an exam type that usually refers to various parts of the body that include breasts, testicles, thyroids, and maybe even some musculoskeletal work. So that's what you'd use a linear array for. The curvilinear array is typically used for abdominal work. It is also used on endocavity probes. And then our vector array or sector array, which is the third one, that is typically used for cardiac work, although it's used in some abdomen work. But the problem with the vector array, as you can see from the image format, is that the near field is very small, and the image quality in the near field on vector or sector probes is suboptimal. And so typically curvilinear probes are used for abdominal and obstetrical work. Let's talk about power or acoustical output. One of the settings on an ultrasound system is power or acoustical output. You can see where I have the arrow pointed. This system here is actually a GE Logic 9. What you're looking at in this image is my gallbladder, and you can see where it says AO and 100%. So I have the system turned up to 100% acoustical output. This is the amount of acoustic energy transmitted, and this is a key word, transmitted into the body. This is how much energy you are putting into the body. Like most imaging modalities, we want to use the ALAR principle, as low as reasonably achievable. For obstetrical work, you typically would not go with 100% output. You would reduce that down. It's typically measured in decibels or percentage of maximum output. Improper settings can reduce penetration. However, when you adjust the acoustical output of a system or power, what happens is the system receivers, the gain on those receivers will increase to compensate. And so with my abdomen, I can actually scan at about 12.5% maximum output and still get a fairly diagnostic image on my body because the receivers over-amplify it and bring that image back up. You typically wouldn't scan at that setting, but I've experimented to see how low I could go with output and still get a decent image on my body. And I have probably an average body for an adult male, and I can go down to 12.5% and still get a decent abdominal image. So the systems do a good job of trying to compensate for a lower acoustical output. It's usually labeled, the button is usually labeled power or output on systems. Gain. This is the other half of acoustical output. This is the amount of amplification of the received echo. So the transmitter's push the energy into the body, the acoustic energy into the body. The energy bounces off structures within the body and then is reflected back to the transducer. The transducer, the elements on the transducer will vibrate, create an electrical pulse, and that pulse is amplified. These are the received echoes, and this B gain, or this overall gain, you're telling the machine how much to amplify those received echoes. These images that you're seeing here, what you're looking at here is my thyroid, top and bottom, and there is no difference in those two images other than I've increased the gain in the bottom image. You can see in the top image my gain is, I believe, it's minus 4 decibels, and in the lower image I've increased the gain to 17 decibels. So exact same image. Now when talking about gain, we also have to talk about DGC and TGC. I use both terms. They're identical. DGC stands for depth gain control. TGC is time gain control. Exact same thing. Different manufacturers call them different things. What depth or time gain control allow you to do is it allows you to adjust the gain, the received gain, in particular areas of the image. What this does is it allows you to, or allows the sonographer to, even out an image and make the image more uniform. Or if you're looking at, say, a blood vessel or a heart chamber, something like that you want to clear out, you can actually lower the gain in that particular area of the image. Frequency. This is something that when I started in ultrasound back in '86, back when ultrasound machines were powered by coal, all transducers had one operating frequency. A 3.5 megahertz transducer was a 3.5 megahertz transducer. It transmitted at that frequency, it received at that frequency. Ultrasound has come a long way since then. Today's ultrasound systems have a multitude of frequencies, and this allows you to tune the frequency to the body part that you're looking at and the body type. You can see the little green arrow in this image here pointing at 14 megahertz. So you can see above that my probe type is a 15L8W, and below that it shows that I'm scanning at 14 megahertz. So frequencies do vary depending on the probe. The probe type typically, with higher frequencies, we're looking at small parts like breasts and testicles and thyroids, musculoskeletal work. Lower frequencies are typically for abdomens. So lower frequencies, the thing about frequency is we get into talking about ultrasound physics. Lower frequencies give you better penetration, but lower resolution because of the wavelength of the pulse going into the body. So the upside of low frequencies is we can penetrate. So a person with a very large body, we would want to go with a low frequency to penetrate that person. But the problem is we're going to lose resolution. On the other side of that is a high frequency is less penetration but higher resolution. This 14 megahertz that you're looking at here, if I were to scan my thyroid and only go in 4 or 5 centimeters, 14 megahertz would be practical. But at 14 megahertz, 4 or 5 centimeters, excuse me, is about all I can penetrate. For a deep abdomen at, say, 18 centimeters to 20 centimeters, we'd have to use 2 to 2.5 megahertz. So there's a trade-off. Modern probes do have multiple frequencies. They have primary frequencies, and they have something called harmonic frequencies, which we'll get into in a moment. Looking at these two images are the same exact image. Identical settings, identical transducer. The only difference is I scanned the top image at 2 megahertz and the bottom image at 4 megahertz. And again, this is my liver and kidney. And I'm not sure how it looks on all of your computer screens, but if you look at especially the texture in the liver off to the left of my kidney, you can see that the texture looks much finer. It looks almost like sand, where the top image looks very coarse. The higher frequency will give you a much finer looking image. And so the rule of thumb for scanning in ultrasound is always use the highest frequency possible for the body part that you're looking at. That'll give you the best resolution. If you can't penetrate with a particular frequency, you need to drop it down a little bit, but always go with the highest possible frequency. Let's talk about Harmonics. Harmonics is something that came out probably about 10 years ago. And what it is Harmonics allows a system to transmit at a certain frequency and then receive at a higher frequency. And what that does, so for example, if I turn on Harmonics, I can scan at, say, 4 megahertz. But what I'm going to do is I'm going to tell the machine to filter out the 4 megahertz receive signal and listen for a harmonic. Every sound wave has a harmonic. So the harmonic of, say, 4 megahertz would be 2 and 8, 1 and 16, 500 kilohertz and 32 megahertz. And so that's the way harmonics work. And so what we do is we send in a certain frequency, we filter out that primary frequency, and we listen for the first harmonic at the higher frequency. And what that allows us to do is it gives us the penetration of the primary frequency, but it gives us the higher resolution of the secondary frequency. So if you look at this image here, what you're looking at here is my gallbladder. The top one is I'm using a primary frequency, and the bottom one I turned on harmonics, and you can see the noise in my gallbladder up top is greatly diminished in the image at the bottom. Harmonics was developed mainly for difficult-to-image patients, but I see it used pretty commonly these days. Most sonographers just default to using harmonics. However, depending on body type, it may or may not look good. I mean, harmonics typically does not look good on me, but body types vary, and it depends on ethnicity, it depends on levels of hydration, it depends on body weight, body density. So I've seen very, very large people be what we call glass bodies, very easy to image, and I've seen very thin people be very difficult to image. But typically, the larger the body habitus, the more difficult to image, and you would use harmonics. Focal or transmit zones. What contemporary machines allow us to do is it allows us to choose where we want to focus the system. In these focal zones where you can see all these arrows in the image up top, we're telling the system where we want to electronically focus. There's two different kinds of focus in an ultrasound system. There's the mechanical focus, and that is determined by probe design. It's the way the array is cut. Every probe has a sweet spot depending on the design of the probe, and there's a certain area where the beam width is the narrowest, and the image is what I call the tightest. It's where the highest image quality occurs, and that is due in part to the mechanical design of the probe. But the other thing that we can do is we can tell the system that we want to electronically focus in other areas of the image outside of where that mechanical focus is. And the way the system does it is through a series of electronic delays within the machine that allows us to adjust the transmit focus. It is user selectable, and a system can have from 1 to 8 or more focal zones. What multiple focal zones allow us to do, it gives us higher spatial resolution and lower temporal resolution. And what that means is spatial resolution is our 2D space. So our 2D image gets much better. The downside or the trade-off of multiple focal zones is it reduces frame rates within the system. And so if you have say you have a cooperative patient, they can hold their breath, or you're doing a part of the body that is not moving and is not affected by respiration, you can use a high number of focal zones. But if you're looking at, say, a heart, or you have a patient that cannot hold their breath or will not cooperate, cannot stop moving, using a high number of focal zones will be detrimental because your frame rates are so low. One of the things I pointed out is, and I'm taking a slight tangent here, but it's something that as ultrasound service people we'll all see sometime in our career. This bottom image here. Hold on, let me computer malfunction here. There we go. This bottom image, you can see I have some arrows pointing to a left to right artifact within the image. It looks like an arc. And that is an artifact created by multiple transmit zones. When we use multiple transmit zones or focal zones, what the system is doing is it's transmitting to the first zone and receiving that image, and then transmitting to the second zone, receiving that image, and then piecing those images together electronically. Well, you can get this artifact down below, and it's a focal zone artifact. This is not a malfunction, and this is nothing you can fix. We get tech support calls constantly on this, where a sonographer will see that and be convinced that their machine is malfunctioning because they've never seen that before, but it's one of those things that they have seen it before, they've just never noticed it. And once they notice it, they can't get it out of their heads. So if you see a horizontal artifact that looks like this bottom image, either if you're on site, turn off multiple zones, or if you have the customer on the phone, ask them to deactivate multiple zones. If that artifact goes away, then we know it was caused by multiple focal zones. Again, this is it's the way the system works. They all do it, and there's nothing you can do to remedy that. Dynamic range, another setting on every ultrasound system out there. Some systems call it compression. It's the range of echoes processed by the system from strongest to weakest. We set this dynamic range based on the body part. A lower setting is less range of grays, and a higher setting is more range of grays. And so you can see from these two images here, what you're looking at here is my thyroid. And for soft tissue, like a liver, like a thyroid, breast, things like that, a testicle, you would want to use a higher dynamic range. You want to see all those wonderful shades of gray. You can see that the top image is very grainy, and that's a very typical sonographer term. My image is grainy. The bottom image is very smooth. We have a lot more information. We're getting a lot more shades of gray. So with a thyroid, a high dynamic range is good. Now if you look at this image here, what you're looking at here is my common carotid artery. Now you can see in the top image, I'm using a very low dynamic range. In the bottom image, I'm using a very high dynamic range. And you can see that the top image, using a lower dynamic range, will allow you to clear out that vessel much better. It allows you to see the walls of the vessel better, and unfortunately for me, that slight amount of plaque stands out a little bit more. Frame rate. Frame rate is something that the system will vary depending on whether you're using multiple focal zones. A lot of systems will allow you to change the image width in order to increase frame rates. If we're doing, say, an echo study, especially on a child, their heart rates are much higher, and so you need very high frame rates for the system to keep up with the motion of the heart. And so by using the multiple focal zones, we're decreasing frame rate. Some systems will allow us to adjust. There'll be a setting called image width that will allow you to narrow the width of the image in order to bring your frame rate up. So our lower frame rates give us better spatial resolution. And again, spatial resolution is the ability, the definition is the ability to distinguish between 2 points in space. Higher frame rates give us better temporal resolution, which is our ability to detect an object's motion over time. And so we want to adjust that frame rate depending on what we're looking for. If we're looking at soft tissue, a low frame rate is fine. If we're looking at a heart, then we want to bring the frame rate up. Space-time or resolution. Systems allow you to somewhat adjust your frame rate by a button. On the Accusant Sequoia, it's called space-time. On some other systems, it's called resolution. So it allows you to adjust the processing power of the ultrasound system to optimize either spatial or temporal resolution. So if you look at the top image looks very grainy. I'm using, this is an Accusant Sequoia, this particular image on my thyroid, and I'm using what's called a T1 or temporal 1. So that's a high frame rate. On the bottom one, I'm using what's called S2 or spatial 2, which is, I told the system I want to concentrate solely on spatial resolution. And you can see that the image is much tighter. The grain is much finer. Edge or pre-processing. A good analogy for edge or pre-processing is it's like the sharpness adjustment on your television at home. My wife and I recently got a new flat screen at home, and me being a techie, I had to go into all the menus and start playing around to her frustration. And I had to adjust the red, the green, and the blue, and I went into sharpness. And my wife's comment was, well, we want it as sharp as possible. And I said, well, no, we don't, because if you make things too sharp, it gets kind of abrasive to look at. and you're actually looking at that on these images here. Edge of pre-processing is a sharpness for an ultrasound machine. That's what it means. And what it does is it sharpens the edges or borders of structures. In the very top image, I'm using the highest edge or pre-processing possible. I'm using a +3. In the bottom one, I'm using a -3. The proper setting is usually somewhere in between. The top image, and it might be difficult for you to see on your computer screens, but when you're watching it in real time, when the image is not frozen, it's very staticky. It's very noisy. The bottom image is very, to use a sonographer term, very mushy. It's very washed out. So somewhere in between for edge of pre-processing is the proper setting. Persistence. Persistence is telling the ultrasound system, I want you to average X number of frames. A single ultrasound frame is very noisy, very grainy. Multiple ultrasound frames can get a little bit washed out, but with no frame averaging at all, the image is very unpleasant to look at. And so we want the ultrasound system to average several frames together. In these two images here, the top image has minimal averaging. You can see the image is very noisy, very contrasty. And the bottom, I maxed it out. So again, with persistence, we want something that is somewhere in between. Normally, these are set by the sonographer, but the you may hear from a sonographer, well, my images are really washed out or very slow. They may have the persistence too high. Post-processing or gray map. Post-processing is just that. If you're using an ultrasound system and you create an image and you freeze that image, you can actually go in and post-process that image. And you can do that by changing different gray maps. That's one of the functions you can do. And what you're looking at here is, again, this is my thyroid. You look at the circular object is actually my carotid. The oval structure above that is my jugular, which is somewhat collapsed here. But off to the right of my carotid, to the right of that circle, is my thyroid. And what I've done in this particular image is all I've done is changed gray maps. So these are the exact same images. There's absolutely no difference. I scanned with the same probe, same settings, froze the image, took the first one with a softer presentation, and then I changed the gray map, and I changed it to a more contrasty presentation. So this is called post-processing or gray map. What the system is doing is you're telling the system, okay, all my intense echoes, I want a really bright white, and all my weak echoes, I want a dark gray or black. And what the system does is it'll map those echoes, and it'll map them any way you want them. And a lot of it is dependent upon the structure that you're looking at and the sonographer's preferences. What you see off to the right is what's called B-color. Color is used on B-mode images and on some Doppler images, which we'll get into in a moment, to make things stand out a little bit more. The human eye is a little bit more sensitive to changes in color than it is to changes in grayscale. And so sometimes a sonographer will colorize an image to make something stand out. For example, if they're looking at a say a mass in the liver, what they'll do is they may turn on that color to see if they can make that mass stand out a little bit. Speckle reduction imaging. This is a feature that is pretty much standard on all contemporary machines today. One of the things about ultrasound images is that they are inherently grainy. And so what the speckle reduction imaging does is it is an algorithm that's within the machine that allows the machine to take away some of the speckles and make images a little bit smoother. All the different manufacturers have it. It's called SRI by General Electric, X-Res by Philips, U-Scan by Mindray. So there's all kinds of different names for it, but all it does is it reduces noise within the image. So our top image is speckle reduction off, and our bottom image is SRI on. Compound imaging. Compound imaging is something that came out probably about 5 or 6 years ago, maybe a little bit longer. And what it's done is, if you look to the right of the two images, and you see that that pictogram, you can see it shows conventional imaging technology and compound imaging technology. Standard ultrasound, the lines of the ultrasound lines, they fire from the transducer, they go straight down, and they bounce off whatever object you're looking at, or objects, and then they're reflected straight back up. With compound imaging, and I believe Philips revolutionized this, they introduced it some time ago, they call it Sono-CT, but they said, well, wait a minute, with CT scans, we are hitting an area of the body from all different angles. Why don't we try that with ultrasound? And it actually works really good. What they do is, through electronic steering, is you're able to steer the ultrasound lines at different angles. And I was actually demonstrating this at the site I'm at earlier. If you have an ultrasound system and you have the probe activated, you can actually turn compound imaging off and put, say, a paper clip on the face of the probe, and you'll create a really bright line going down the middle of the image. And then if you turn on compound imaging, you'll actually see the system firing at all the different angles. It's actually kind of cool to look at. So the next time you're in front of a machine, I encourage you to do that. It's a really cool technology. It allows for improved image quality. It does reduce noise, and especially for irregularly shaped structures, it makes them stand out much more. General Electric calls it crossbeam. Philips calls it Sono-CT. If you look at the two images, the top image is compound imaging off, and the bottom image is compound imaging on. This is pretty much standard on all contemporary machines. Let's talk about different imaging modes. This is called B mode, and actually this ultrasound image here is an early ultrasound image of my son. So B mode is basically a two-dimensional image. So sound waves are sent into the body, they're reflected off anatomy, and the intensity is analyzed, and a shade of gray is assigned to that particular echo. M mode stands for motion mode. M mode is typically used in the heart. So what the sonographer will do for either an adult heart or a pediatric heart is they will fire that line of sound down through the heart, through the valves, to determine valve motion. And you can see these waveforms, which I am not sophisticated enough to read. This cardiac scanning is a whole different animal. But what it allows them to do is determine valve motion, and it also allows them to determine if areas of the heart wall have died. So if somebody has a heart attack, a portion of the heart wall may die, and they'll be able to tell that the motion part, or that part of the heart, the motion is not as dynamic as the surrounding tissue. So M mode is motion mode. Now we have Doppler. Doppler is really cool. The way Doppler works is very similar to a police officer with a radar gun. A police officer will sit behind a billboard, and as you're coming down the highway, he or she will hit your car with that radar beam. The beam bounces off you and goes back to that gun, and that gun says, okay, I have a Doppler shift of this. I know that person is coming towards me, and I know exactly how fast they're going. We can do that with ultrasound too. What we do is we take a signal and we send it into a blood vessel, and we bounce that signal off red blood cells. And we receive that signal back, and we can tell by a frequency shift what direction that blood is going in and how fast it's going. There's various forms of Doppler. The top Doppler that you see is a combination of color Doppler and pulse wave Doppler. The bottom image is something that's called either power or energy Doppler. There's also a continuous wave Doppler that is used for cardiac exams. This is something that we see on a fairly regular basis. The purpose of this presentation is not to turn you folks into sonographers. And that takes years of study to do, but what I want you to do to be able to walk away from this from this with is the ability to recognize some of these things, and this includes Doppler aliasing. I've received countless calls over the years that my Doppler is defective. It is reading inaccurate frequencies. It's showing me pathology where there is no pathology, and there's something called aliasing. When an ultrasound system is not set up properly, what will happen is the ultrasound signal will do something called wraparound, and it occurs when the velocity of the blood exceeds the system's ability to display it. Can this be remedied by a scale or PRF adjustment? If you look to the left of the scale here, there you see the numbers 0.30 and 0.10. That is our scale or PRF adjustment. What we can do is we can adjust that to make to accommodate the faster Doppler signal. If you look at this image here, you can see that our Doppler signal is going up to the very top of the graph and then wrapping around and coming in from underneath. This shows us that we have the system not adjusted properly. And this is called aliasing. Color Doppler can also alias. When Color Doppler came out, it was referred to in a derogative sense as Doppler for dummies. Pulse wave Doppler is a little more technical to read. Color Doppler is very graphic. And so the reason Color Doppler came out is if you look at the very top image, this is my carotid artery and my jugular vein. The red is my carotid. And Doppler came out, as I mentioned in the previous slide, when with the ultrasound system we can tell what direction the blood is going in and how fast it's going. And so we can see by this top image that the blood is going in all one direction. Now, if I had some pathology there, say I had a large piece of plaque within that vessel, what would happen is the blood cells would hit that plaque, and they would start. It would create some turbulence, and within that turbulence, some of those cells would end up going backwards for a short period of time. Well, that would recreate a reverse Doppler shift, so you'd actually see blue within the middle of that vessel. And that would say, hey, there's some pathology here, there's plaque here, we have blood flow reversal. That's a bad thing. If you look at this bottom image, that is my carotid as well. You can see all that blue in the middle of my carotid artery. I didn't automatically induce plaque into my artery. All I did was I took my Doppler scale and I adjusted it too low. And so by adjusting it too low, I was able to make the system look like it's malfunctioning. And so it's a little challenging to determine this, but I just wanted all of you to be aware of the term and to be able to recognize it when you're looking at a machine. If somebody complains about ultrasound color Doppler inaccuracy. So in the top image, I set the scale properly. The bottom image, I intentionally adjusted it improperly. And you see, note the color wraparound. If you recall from the previous slide, that pulsed wave or that waveform, it wrapped around that graph where the peak was being cut off and then the peak of that graph was coming in from underneath. Well, what you're seeing here is if you look at our color bar off to the left, you see our slowest velocities are like a dark red, and then the faster velocities go up to a yellow, and then imagine that wrapping around and going into the bottom bar where we're seeing our blues. So we're actually wrapping around with our color Doppler as well. Artifacts and dropouts. One of the most common things that we'll see as ultrasound service providers. Again, I'm off site today. I'm at a customer site, and we were off looking at several ultrasound systems this morning, and a few of them had dropouts, and we were determining whether they were probe or whether they were part of the machine. So we were actually doing some of this work earlier today. But artifacts and dropouts are a very common reported problem. You can see that slight artifact in the near field of the probe. We need to start looking at, what is this? Is this caused by the actual array of the transducer? Is it the cable? One of the things that we do, it's a field test, but you can take a metallic object. I like to use a ballpoint pen. I carry a pen that's made out of metal that I can roll across the face of a transducer. A paper clip works very well. You do not want to use any object that is sharp because the lens of a probe is very delicate. So you want to use something that is rounded. A screwdriver works well, not the tip, but the shaft itself if it's round. But you can actually slowly move that metallic object across the face of a transducer, and it'll create a very bright beam within the image. If that beam fluctuates as you're moving it across, that will tell you that you either have a weak element, a dead element, or perhaps a bad cable. One of the ways to tell if you have a bad cable is you can activate the Doppler function, and when the Doppler is on, you can take and hold the transducer by the strain relief up near the scan head and slowly flex the scan head back and forth, kind of rotate it around in a circle in each direction. And if you induce noise within that Doppler signal, you know that you have broken cables within that neck. We also want to look at the probes and the pins on the probe, the connector. One of the things that, as a service provider, I constantly did every time I got in front of a machine is I always examined the pins on a probe. The pins get bent easily. If the probe won't get plugged in, the typical reaction is, well, push it harder, jam it in, it'll go. And what that does is it damages pins. There's multiple problems with that. If pins are damaged, that's a bad thing. We can fix that. We have the ability at Conquest to fix bent pins on transducers. The problem happens if somebody bends pins on a probe and doesn't catch it. What happens is then they plug that probe into a system, and now they've damaged the connector board on the system. So now you have a bad probe and you have a bad connector board. But it gets worse. The sonographer will then unplug that probe from that connector and maybe plug another probe into that connector. So now we've damaged another probe. But then it gets worse from there. If it's in a large hospital, what they may do is they may take one of those probes and move across the hallway and plug one of those probes into another machine, thereby damaging that machine and starting that problem all over again. So we want to make sure, if we do have an artifact or a dropout, that we're examining all the probe pins and the connector board on the system. And then we want to look at front-end boards. So if we've isolated the probe, okay, the array is fine, the cable is fine, we've tried a different probe, we still have this artifact. At that point, we have to start looking at the machine. Is it within the front end of the machine? And what I have here is I have various block diagrams for front ends of the systems, and we're not doing system training today, so I'm not going to spend too much time on this. But you can see from this is the Accuson Sequoia. Not a lot of Sequoias out there still, but I'm sure there are some at some of your sites. You'll notice that the Accuson Sequoia has multiple TX, which are transmitter boards, and multiple BFs, which are beamformer boards. If you have an artifact within a machine, you can open up the system and rotate your transmitter boards and then rotate your beamformer boards and see if the artifact moves. If it moves when you rotate the transmitter boards, you know it's one of those TX boards, and same with the beamformer boards. So you can actually use the parts within the machine for troubleshooting. Same with the Philips IE22 and IE33. The channel boards. There's 4 channel boards within a 22 and 33. If you have an artifact that you've determined is not caused by a transducer, you can actually rotate those channel boards to determine if a channel board is causing that artifact. GE Logic 9, same thing. Those looks like my labels disappeared, but those 8 white rectangles are all time delay boards. And so again, with the Logic 9, you can rotate those and see if your artifact moves. Again, so you're using the system to troubleshoot an image artifact problem. Here are some common artifacts that may be reported by sonographers. These are artifacts that I've had to deal with in the past. These are not malfunctions. These are a result of physics. It's just the way the systems operate. And I just wanted to go through a couple of these, so if you do see them, you recognize them as not a malfunction of the system, but as just the way the system works. And understanding a lot of these things will help you going forward when you are troubleshooting. I've had countless tech support calls over the years where people have tried to troubleshoot problems on systems that are not malfunctions. It's just the way the system operates. This particular one is called the reverberation artifact. And the reverberation artifact, it's echoes between 2 bright reflectors. So if you have 2 bright reflectors within an image that are very close together, the echoes will repeat, and you have that kind of staccato pattern going down through the image. Okay, I see we have a question, and I'm going to bring that up.
Okay, Matt, just to chime in here, the question that's come through is, was that an, and I apologize, artrocyte or bituminous coal ultrasound machine? ANTRACITE or BITUMINOUS?
Oh, they're, I believe they're referring to anatomy and not specific types of machines.
Ah, okay.
And I'll be completely honest, I don't know the answer to that.
Very well. Fair enough. Continue on. Thank you.
Thanks, Kristen. Man, the first question and I get stumped. How embarrassing. We are going to have a Q&A session at the end. Hopefully the next one will be a little bit easier. I have a feeling there's a sonographer out there attending this. And whoever that is, you're banned. So the reverberation artifact, that can be echoes repeated between two bright reflectors. And so you can see that repeated pattern of echoes. And this is normal and not a malfunction. Shadow artifact. You can see this artifact in this image here. That is I believe, a gallbladder, and there is some sludge within that gallbladder. And you can see that dark area below. That is that dark shadow. That is a normal function of the system. That is not a malfunction. And that is not my gallbladder, by the way, thankfully. And then artifacts and noise. This is actually this is very timely. The site that I'm at today is experiencing noise in a couple of departments on a couple of different machines. One is a Philips Epic 7, and the other one is a Philips IU22. Not that I'm bagging on Philips. They all experience them. In fact, the images that you see in front of you now are a GE Logic 9 that was experiencing some noise. Noise problems are by far the most difficult problems to troubleshoot. We're going to, in fact, after the webinar, we're going back up on the floor and we're taking one of the systems for a drive, and we're going to be moving it around the hospital and try and trap this noise problem. But over the years, by far the most difficult problems I've encountered have to do with noise. And so you can see in these images, when you see an artifact within the image, you want to start asking yourself, or the sonographer, hopefully, some questions. And you want to start with, is the noise moving? The vast majority of noise is dynamic, and so it'll be moving throughout the image when the image is unfrozen. Did I lock up? I locked up. Bear with me. We have a computer malfunction. There we go. We're back. All right. Can you isolate the system by unplugging all potential noise sources? And so when you get this noise artifact on the screen, you want to look at the system itself. Are there peripherals? And a peripheral would be a VCR, a black and white printer. I know, this is kind of old school stuff. Most systems don't have those things connected to them these days, but systems may have an external monitor in the room that is connected to the system. There may be a network cable, in all likelihood, that is connected. So can you isolate the system where it's just the system plugged into the wall, nothing else connected to it? And by removing those things, has the noise gone away? Now you want to look at power. Can you try a different power source? Try a different plug in the room. One of the things that we looked at today is, one of the questions I asked regarding the noise at the site I'm at today is, when the sonographers go on portables, are they plugging the system into emergency plugs? So that's one of the things we're going to look at this afternoon, is the power sources that they're using. Is the system ground intact? The clinical engineer that I talked to today regarding this noise, one of the first things I asked him is, have you done a ground continuity test? And he said, well, yeah, I've already replaced the power cord, so we believe the ground is intact. But if you look at this image here, or these two images, this is a GE Logic 9, and you can see it's kind of hard to tell, but there is some 2D and some color noise. You can see the color noise speckle in the lower image. This has to do with the card cage cover ground not being intact. On the GE Logic 9, this is a fairly common problem where the area between the card cage cover and the card cage becomes oxidized, and the solution is to just clean all contact areas and this noise will go away. But we want to start examining system grounds. Is the system grounded properly? And what about the facility ground? I was sharing with the clinical engineering department at the site I'm at today a unique problem I had years ago where a system was manifesting noise and we replaced everything on the system and could not get the noise to go away. The solution, and this is a true story, was actually finding the building ground and taking a garden hose and trickling water on that ground overnight to have it better conduct noise to ground. So the facility ground can actually be a problem. And can you move the system to a different environment? By taking a system and moving it to a completely different part of your facility, it isolates several things. It moves it to definitely a different power circuit, and it gets it away from any EMI or RFI sources. So it's a totally different environment, and that'll help you determine, well, is the noise source internal or is it external? And that is the end of the presentation, and we're going to open it up for questions.
Great, thank you, Matt. We've got a few here. Let's see, the first one, why would emergency power sources be better or worse for portable ultrasound?
Well, the emergency power source, it is a different circuit, and so it doesn't necessarily have to be worse. It's different. And by going from an emergency source to another source, we know that we're going to a different circuit. And that's part of that isolation process.
Okay, we have another one here. What is the typical savings comparing Conquest over the OEM for service?
Well, for overall, one of the things that Conquest specializes in is migrating service in-house. These comprehensive programs where we work with organizations to bring their service in-house and utilize Conquest as a support structure. Typical savings are around 40% over the OEM, and that doesn't include some of the soft savings like improved uptime and customer satisfaction.
Great. The next question here is, with the systems being computerized, shouldn't they be put up on power systems? I'm sorry. Yeah. With the systems being computerized, shouldn't they be put up on power systems?
They're probably talking about either surge suppressors or UPSs.
Yes.
And the manufacturers actually do a pretty good job of building that circuitry into the systems. I was with I was with a major manufacturer from 1999 to 2002, and one of their initiatives was selling a UPS along with every ultrasound system. And I did an experiment, and I did a power analysis of wall power in a facility versus the output of the UPS, and the UPS power output was actually dirtier. So I guess it would depend on the UPS. If you have a really good one, it's probably not a bad idea, but the manufacturers actually do a pretty good job of protecting the systems. I haven't seen. I should say the frequency of systems being damaged by power I've seen dramatically decrease over the years.
Okay, the next question is, what standard do you use to do a PM on an ultrasound unit?
That's a great question. It's not standard, it's standards. There are so many different regulatory and accreditation organizations out there now that it's very complicated. On the regulatory side, we have the Joint Commission, we have the new CMS directives, and then on the accreditation side, we have ACR, which is the American College of Radiology. We have AIUM, which is the American Institute of Ultrasound and Medicine. We have IAC, which is the International Accreditation Commission. And so we have all these different organizations to satisfy when we do a preventative maintenance. So what we've done at Conquest is we've developed a comprehensive PM process that satisfies all of them, because we don't know when we're going into a site to perform preventative maintenance. A lot of times the site doesn't even know who's overseeing their accreditation. And so we make sure that we satisfy all regulatory and accreditation organizations.
Excellent. The next question is there a required phantom for ACR accreditation?
There's not, and that's where ACR gets a little tricky. ACR asks you to do sensitivity measurements with an ultrasound probe. So they say pick a probe, any probe, and they want you to do sensitivity testing. So they want to know how far or how deep that probe is penetrating. Well, unless you're adept at scanning yourself and can truly do that and find the noise floor on your own body, you need a phantom. But yet there's a section in their annual evaluation that says the phantom is optional. So they're making you do a test that probably in all likelihood would require a phantom, but then they tell you a phantom is optional. I highly recommend having a phantom, because you actually have to do measurements during ACR accreditation. You have to measure on the lateral plane and the axial plane 2 different pins to make sure that the system measurements are accurate. And I don't know how you can do that without a phantom. We recommend the ATS 539. It's manufactured by a company called ATS. Linda Hammond is a friend, and she owns the organization. By far the best phantom out there, in my opinion. They're not sensitive to temperature. They're bulletproof, and they're very cost effective. So anybody who does need a phantom, we distribute the ATS line, or you can go directly to ATS.
Great. Okay, another question that's come through. What could be the problem of our newly acquired Sonoscape ultrasound booting the system hang?
It's probably software. Contemporary systems are all, they run layers of software. They're all running Windows. And so it could be the Windows software hanging. It could be the Sonoscape software hanging, because the Sonoscape software is running on top of Windows, so Windows has to fire and fully initialize, and then the Sonoscape software starts firing. So, it would depend on where in the boot sequence it's failing. If there's a progress bar, or if there are any error messages, it's hard to determine without additional information.
Okay, and one last question I think here before we wrap it up. Will using ADR or UPS improve the resolution or reduce the noise?
In my experience, no. I haven't seen a UPS reduce noise at all. The systems today do a very good job of shielding out noise. The probes are shielded and sometimes redundantly shielded. So unless you have some type of powerful RFI or EMI noise source close by, I don't think any of those devices would make the image quality any better. Okay,
great. Thank you, Matt. Thank you again to today's sponsor, Conquest Imaging. Please visit their website, conquestimaging.com, to learn more about their products and services. Attendees, remember to obtain your certificate of attendance. You must complete the post-webinar survey at the conclusion of today's presentation. This survey will appear shortly on your computer screen. If you do not receive the survey, email us at webinar@mdpublishing.com. Please visit onetechnician.com/webinars to register for our next webinar Wednesday. Thank you again, and enjoy the rest of your afternoon.
So that's a wrap.